Okay, welcome to our April Structural Modeling video conference. Today we have a number of activities and items to go over and discuss. And one of the primary things we're going to talk about today is the current state of the structural modeling software. We've been working on this particular software set for a little over a year now. And we've established a language, a method, and a context within which we can talk about the different software features. And that essentially was supported by the augmented model exchange isomorphism, which allowed us to talk more precisely about the various relationships between natural language relationships and mathematical and graphical representations. From that, then we did a 19 by 19 city ordering problem, which essentially was a problem that was asymmetric, transitive, and irreflexive. But it only allowed one city at each level, but that gave us enough of insight and enough to work with to create a small web application and to get some discussion focused on that. What we'll be talking about today is an improvement on that specific set of software that allows us now to adapt the size of the matrix, and essentially what that means is that you can have more than one city at each level. So you could, going into an unknown situation, you could have all the cities at the same level. This particular software will adapt to that. We'll demonstrate that. And then we'll also show the same software dealing with the original type configuration where we have just one city at each level. Good morning, Kevin.
Good morning.
And so as we go through the process of discussing this, we'll also place this activity into the context of the SDDP process. And let me bring that up. I'll bring up the graphic here, share that, so we can talk about that a little bit. So in the SDDP process and how we're relating to that specific activity right now, we have steps 1 through 5 are part of the structured dialogue design process, and the ISM process is listed here, steps 6 through 8. Now what we've been working on is the ISM process with the mathematics and the matrices. So we'll be working with step 6, step 7, and then we've demonstrated ways to extract a multi-level graph using some mathematical software packages. We haven't incorporated that directly into the software we have now, but that is something we have demonstrated how to do that. So essentially, we've been working on steps 6 through 8, and we've been working with a irreflexive, asymmetric, and transitive type of relationship. So once we start looking at steps 1 through 5, and especially the interface handoff between step 5 and step 6, this will be an important area to understand what that interface needs to look like. But we'll start working now with with other relationships maybe that have a symmetrical aspect, like the influence. Influences can be both ways, can have a symmetrical approach, and I think we need to start creating a consensus about how we should address that specific problem space next.
Okay.
Kevin,
Yeah.
you had a comment.
No.
Oh, okay. All right. So essentially, we'll be looking at this, but I guess now I think maybe what I'd like to do next is to go here and give a quick demonstration on the software. So let's see if I can share this screen, the whole thing here. Screen share. Yeah, here we go. Let's do it this way. Okay. So some things to note about this particular piece of software. It's written in JavaScript, and it's works only right now on Firefox browser. That's because we're using some features of the newer JavaScript and the newer technologies that are not fully supported in the other browsers yet. And also because we're using the Selenium IDE, which is an automated testing type of tool that's only available in Firefox. So the activities that I'll show here were recorded in Selenium IDE, and we'll simply play them back, and you can play them back and forward, back, stop, look, talk about them, things like that. So this is the general structural modeling grid that will support different applications, more than one city at each level. It'll support one city at each level, or it'll support all cities at each level. So let's look at what all cities at each level looks like for the 19 by 19. And I'm going to run a test script now where I recorded this. Let's see how this works. Okay, so here we have, so the thing to notice is in the same level process pointer here, it's yes, all of these cities are at the same level. And as we can see, we go through here, we ask the question each time, we get that information, and then it creates one vector and says, oh, all of these cities are at the same level. So when we wind up, we really have nothing to order. So this is the boundary condition where everything is at the same level. We cannot make any distinctions with the relationship that we've discussed or selected. So we really have nothing to order. We only have one thing.
Why are there numbers other than 1 and 0 in the cells?
Okay, let's go back and look at that. So you mean like right here in the red, in the orange one? Right here?
Yeah.
Yeah, so yes, right. That's absolutely true. Let's go back and just look at this. Let's just look at this by hand. So when we start with the initialize the city grid, we have an initial city grid that's 19 by 19. And that's all zeros, right? We have no information about the relationship of these cities except we know that they're not north of themselves. So let's go here into the, say, are they at the same level? We'll say yes. We know that city, let's say city 1 and city 19 are at the same level, right? So we'll enter data. Okay. So what happens here when you do that, you see this vector that popped up down at the bottom says 1 and 19?
I see. I thought that the orange row was an item, a city row, but it's It's got a what is it? I can't quite read it. What,
Okay,
what is what does it say in the left-hand column? B1 or,
V for vector.
oh, vector.
Yeah, V1. And so what happens is, you see we have row 1 and column 1 still, right,
Yeah.
in the matrix. And but we don't have a 19. 19's gone now. And so 19 and 1 are at the same level. So we're using 1 to represent the combination of both the city 1 and the city 19. So this row 1, represents both city 1 and city 19.
Why do you call it a vector?
I just, I called it a vector because that's the data structure I programmed it in. You could call it anything.
Yeah. Okay.
So if you think that there's a better name,
Well, is it a level, or is a level something that gets processed later?
Okay, so that's a really good question, and I'm going to try to parse it out before I answer it. So the levels within the relationships, yeah. Let's say for example, like we did with the planar graphs, did the planar graphs and put those together, and those levels are essentially a little bit different than what's going on here. And in this case, what's happening with the city 1 and the city 19, right, in this case, what's happening here is that city 1 and city 19 are actually becoming an equivalence class. So given the relationship that we're using to order these, city 1 and city 19 are equivalent. And so this equivalence makes that where that one city could be an item on an equivalence level chart, but city 1 and city 19 under the relationship of at the same latitude are basically equivalent. So it's a little bit different than level.
When you ask if something is the same level,
right?
Is it filling in assertions in both directions, and that's why it's an equivalence? Because suppose it's another relationship,
right?
Things can be at the same level without being equivalent to each other.
Right. So maybe in this particular case, if we would say the same latitude, would that be clearer? Because I think what we're talking about here is we're using a measure of north and south, right? We're using north. That's the relationship. Is the city north of, right? Is the city south of? That's the relationship we're using. And that's what we're asking here. When we say same level, we're saying, oh, are these cities at the same geographic, latitude? And then when I hear you talking, you're talking about the level within the structure of the matrix.
Yeah.
So I think maybe
when you say yes on the same level, is it filling in Is it fill in two cells of the matrix with ones?
No, it doesn't do that. What it does is it changes the dimensions of the matrix. See, the matrix dimension changes. So let's do another one. Let's say city 1 and city 5 are at the same latitude, right? Here's that data. You see, what happens now is the size of the matrix changes.
Because you're condensing it through equivalence. right?
Right. So what we're doing is we're making equivalence classes. So we don't have a matrix of cities, we have a matrix of equivalence classes.
So this is going to generate a total order instead of a partial order?
Well, it generates a total order of equivalence classes,
Yeah.
but if you analyze the complete structure at the element level, then you have a partial order, because the total order is only at the equivalence class level, right? Each element, each equivalence class is ordered. If you look at a partial, you can look at the same data and look at it as a partial order by looking at the individual elements in each class. So you can look at it both ways. And we can do another one. Let's just go, say, 10. You guys are at the same level. Okay. So anyway, that's what happens. The matrix represents the equivalence classes, and if you want to look at partial orders, then you just plug in the vectors where they go. All right. Now let's go back and look at the look at an example of the original test. So we did the original 19 by 19, and with only one city at each level. Put that together. And let's see, what did we have? Let's open a test case here. I'm going to bring up a test case. Open that. Now that we have the test case, let's see if we can run it. Okay, so now this is the test case where we order the 19 by 19, one city at each level, and we go through, and this comes out to be the same one as we did in the other software. It just shows that this particular piece of software is adaptable, and we can do both. We can do not only the total order, but also no order at all, or a partial order. That's why it's called an adaptive total strength partial order, because it'll handle them all. So as we go through here, you see detect a strategy in filling these out and figuring out how to most effectively search and find out which is the best candidate for getting the next bit of information. And I'll go ahead and let this particular process complete. Then I'll run it again and then discuss a little bit about what that strategy was in this one. I think I've developed one or two other variations on this first strategy, but we'll talk about that as we go. So we're going through and collecting data and then working the matrix. And of course,
what do the buttons move data mean?
okay, with the move city data, we'll go ahead and once this goes through, we'll go back and we'll look at that specifically. But what that means is that if you notice the matrix, right? If you look at the matrix, what we know about the matrix and what we know about this relationship is we want all the ones in the lower triangular piece, right? We want all of the ones down below and all of the zeros we want in the upper triangular. That's the structural information that comes from the type of mathematics we're using. So the move city data, if I enter to a pair of cities and the green in that initial entry is in the upper triangular, I get a green 1 in the upper triangular, then what I do is there's two buttons come up and say, is the green in the lower or is the green in the upper? And if the green is in the upper, what happens is those rows and columns will be swapped to put the green into the lower section. In that particular process where you manipulate the matrix to get all of the ones into the lower triangular piece, when you do that movement, it's possible that you then move other ones into the upper triangular. And if that particular initial manipulation or adjustment of the matrix moves more ones up into the upper triangular, then you click on process data, and then process data will bring up the buttons that says move city data and done moving city data. And then you use the move city data then to go through and move all of the ones, all of the green ones or blue ones from the upper triangular, you move those to the lower triangular. And then when you have all of the ones in the lower triangular, then you click the button done moving city data. That makes sense? Okay.
Yeah, it makes sense.
All right. So basically, we're using some macro global structural things that we know about this particular approach. So let's run it again, and I'll talk a little bit more about. Okay. So what we're doing here is we're starting in the upper left-hand corner, and we're starting to ask the question, is City 1 north of City 2? Is City 3 north of City 4? So we're starting with the upper left-hand corner, and we're starting to order those. The first cities, we're starting to get data on those, and we're starting to order them. Now, when we do that, we then know that we actually, the cities that are above the area that we're asking about are ordered. So we can actually then apply the idea of a binary search to those ordered ones, the ones that are ordered above it, and look for the best, most efficient way to determine if a city is north of another city. Because here we don't know the relationships of these cities, and so we're asking, but we don't know which city to ask about. So we're searching for that in this particular problem. So these recordings basically record and play back the process. And one of the things that's really good about this, of course, is that if you're running a session, you can record the session. And if you make a mistake in the session, you can simply stop, bring the script up because the script is basically in text, edit the text to correct the problem, and then move on. So it's a fairly useful tool, but it's designed for testing. So these are just the first two preliminary test runs I've made at this, and we need to develop more tests, some standard tests on standardized types of relationships, and so I was hoping to get some discussion on that today also. So it was so that's kind of the way that works. Now if we look at the end result here, and this kind of just became clear to me today, we notice we have the 1, 2, 3, So what do we have? Yeah, we've got 1, 2, 3, 4 of these rows that don't have a green below the red. And the reason for that is the system knew that this 13 was right at the right place, but in reality, you actually have to ask that question. You have to ask the question, is row 2, or city 2 north of city 13? And you get a yes, and then that would fill in a green 1 here. So I'm going to, the next version of this, I'm going to add that to where that we'll have green 1s on these. Of course, I would add 1, 2, 3 green 1s. You wouldn't need to do this one because that's the last one. It adds 3 more data points. But this is fairly efficient, and it I haven't looked at the numbers yet or compared this approach to the approach I used in the last one, but they look fairly similar. So that's kind of where we are right now with this. And any more questions?
Can you let it run more slowly so I can see what the interactions are on the right-hand side with the level, rows, enter data, move? I couldn't quite follow. It's going too fast.
Oh, sure, I can do that. In fact, so let's do that. Let's just make this smaller, make it slower. There we go. And we'll run this now on these are just trying to give you an impression of how it works.
Yeah, can you slow this down a little? I can't follow it.
Sure,
So,
I can slow it down.
So it
I can slow it down.
It starts with initializing the grid, and then it asks if something is the same level. If a row and column entry is the same level.
Sure. Let's just let me see if I can step through this one at a time. How about that? So let's see if we can do that. I haven't tried doing that, but let's see if we can do it. Okay. So we have this one. Now let me go here. And okay. So what I have now is I'm going to go here. I'm going to go to Tools, and I'm going to bring up the IDE, which just disappeared. There we go. And then let's go over here and open the test case. Bring up this test case. Let's open that. All right. So let's see if we can. Yeah, okay, so I'm going to see if I can step through this now. So, okay, I'm going to make it slow, and then I'm going to start it, and now I'm going to see. All right. So is that slow enough?
So it starts at the same level, and then, or the question is are two cities at the same level? Is that
right.
The first question?
And that's the first question, and in this particular case, the answer is always no, because there's only one city at each level.
Okay, so it allows you to enter data, process data, or infer information. So
exactly.
if you're going to assert a yes, that would be entering data.
If I was going to assert a yes in the same level?
No, if it's not the same level, enter
Right.
data puts a 1 in row 5, column 1.
Yeah, so, okay, let's go ahead and let's stop the script and just go ahead and do it by hand. And we'll just walk through it, some of that by hand. Take a look at that. See what that does. So let's see. We've initialize the city grid, okay? And we say, all right, row 2 is north of, yeah, city 2 is north of city 1. Okay, so let's enter that data. So you see we entered that data, and we see we have the green is in the upper triangular piece. And we say, okay, let's green in the upper. So we click that. All right. Now, if we say same level, yes. We have these are at the same level. Let's say row, let's say row 4 and row 19 are at the same level, right? Let's enter that data, okay?
Yeah.
And then brings it up.
So you've done what I interpret just happened was there was a 1 entered in row 4, column 19, and a 1 entered in row 19, column 4, and then you condensed the matrix and listed the vector.
That's one way to conceptually think about it. That's not essentially the way that's not the way the software does it. The software doesn't maintain multiple matrices, but it generates them. But conceptually, you're right. Conceptually that's what's going on.
I've never seen the different packages I've seen that implement ISM. I haven't seen this option. Usually, if you want to indicate something's at the same level, you have to make 2 entries. You have to basically enter the complements. If it's row 4, column 19, that gets a 1, and then row 19, column 4 has to get a 1, and then they do a matrix condensation. So it's just a different format than I've seen before. So then, so after what's the difference between processing the data and inferring information?
Okay, look. So what we're doing here is entering the data. That's a main process where we're gathering new empirical information and entering it into the matrix. And then process the data. Process the data comes into play when we have 1s in the upper triangular area. So once we're going through our entering the data and green in the upper, green in the lower, answering those questions, if we get to a situation where we have 1s in the upper triangular area, then the process data screen is used to go through and manipulate the matrix so that all the 1s are in the lower triangular area. And the infer information, that's used to calculate the blue 1s. And to say, okay, anytime in this process you want to know what if there's more inference points that you can get, you just hit that and it infers what those are.
So another word for process data would be to sort the rows and columns into lower triangular form.
Yes, you could say that,
and then inferring is multiply the matrix to get the reachability.
Basically, what happens with the infer information is you take the structure matrix, which does not have the identity matrix with it. And so you have a structure matrix, you make a copy of the structure matrix, you add the identity matrix to the structure matrix, and multiply that to get the reachability matrix. And then you take the reachability matrix and the original structural matrix, you subtract those to get the blue ones, everything that was inferred.
I see. Okay. That makes sense.
Yeah, so it's fairly straightforward. It's again, it's the asymmetric approach. We haven't done the symmetric approach, and that's what I would like to get some insight on how that would be different, and what would be maybe some test cases, and even some some data sets that we can use to try to start addressing that.
I've never where the the systems that I've seen, symmetry is indicated by answering in both directions of the relationship. So you have, like I said, as I said before, row 4, column 19 has a 1, and row 19, column 4 has a 1, and that's what gives you the symmetry. But I'm not sure what you mean by symmetry different than that.
Okay. Well,
or what's the difference between symmetry and saying they're at the same level?
Excellent question. So, in this particular case, when we're looking at is north of, and we're talking about cities in space, in geometric space, we're saying these cities are at the same latitude. Therefore, they're equivalent. Right? That information that we have, that city, let's say 1 and city 19 are at the same latitude, we spend the resources, we get that information, we find out they're at the same latitude. Therefore, for the relationship is north of, that gives us no, that gives us no information about that because they are equivalent. Gives us no information about the order, except that these two things, these two elements in the set themselves, are at the same level, but they tell us nothing, about the order to how they relate to everything else.
But you're in this, so you have a reference point, like an absolute scale reference point in the background information. So you're saying if you know the two cities are at the same latitude, then you say same level, rather than.
I'm saying they're equivalent. They are equivalent for this.
Right, but usually the style of inquiry is bottom up, and you only know the relationship of cities with respect to each other.
Well, that's what we know that, and that's what we're doing here. But when we say they're equivalent, right?
Well, it's a good question because it's different to say they're equivalent. To me, implies that you know something about their latitude, versus saying is city A north of north of B and south of C, and is city D north of 1 and south of C, and that's different. So that doesn't mean they're at that A and D are now at the same latitude. It just means they're both in between A and C. So there's
I think that the point here is, and I think it's an important point, and that is, in the original software where we said only one city at each level.
Yeah.
Then we asked the question, okay, is city 1 north of city 2? And if that was yes, then we had some information. And if it was no, we had the same information. Because at one city at each level does not allow them to be at the same latitude. In this case, we ask, is city 1 north of city 2? And then we have to ask, if that's no, then we have to ask, oh, is city 2 north of city 1? And if that's no, that means they're both at the same latitude. So you have to ask the same question twice if the answer is no.
Yeah.
If the answer is yes, you've got your answer. So that's what same level means. Actually, you've had to ask that question twice.
Right. Okay.
And but this is an asymmetric relationship, right?
But I think just for when you explain this, to introduce the notion of latitude puts an absolute scale where on it implies it, but the only way we really asking about the information, we're not asking about latitude, we're asking about the relative position with respect to each other.
Yeah, okay.
I just think for, as we're moving towards, as you move towards publication, we have to be careful about that because it's introducing another measure.
That's true. That's true. This is rather informal. We'll tighten it up as we go. But the influence one is the one, the influence relationship is different than the north of relationship. It has different logical properties. And so that is one that I would like to start thinking about addressing next.
What do you mean they're different? It's still a partial order, right? I mean, additional properties beyond being a partial order?
The influence one basically is symmetric. A could influence B, and B could influence A. That's essentially a symmetric, whereas north of is asymmetric. So, so what we're going to do there is explore that and see if they are different or if they can be treated essentially in the same way. But as we do that, because we're not looking directly at the natural language words, but we're looking at the group of logical properties, then what we can do is start creating groups, if we have to, of different software approaches that relate to each one of the logical property groups. I'm not sure we need to, but maybe we do. I've seen some areas that seem to be people have tended to struggle because they're trying to maybe apply their technique to a natural language relationship that it simply doesn't have the logical properties to support.
Right.
So that's kind of the idea.
Right. Okay.
All right. So we got that part. So let's see. The other thing that I was going to look at that. Take a look here briefly at the read ahead. Talk about that a little bit. which is right here. Share that. Okay, so essentially what we've been doing is looking at the aspects of structural modeling that blends formal information with empirical information. And adding that up, adding some specific approaches, looking at some classical applications, and then looking at the idea of the ordering, the partial ordering. And I think that the primary thing is, if it's truly unknown, your technique and your approach needs to be able to adapt to that unknown type of ordering. So we went through and looked at the ISM work. We developed the AMEI. I think the augmented model exchange isomorphism is kind of the foundational piece that we kind of relate back to if we need to actually develop new mathematical techniques for different types of logical classes. Then we would relate those back to those logical classes. And then if that was the case, we'd also maybe get some insight into why that was the case.
Joe, I have a question on page 3.
Sure. Okay.
In the first set of bullets there, it says a partial order on a set has reflexivity, antisymmetry, and transitivity.
Right.
And I thought a partial order was irreflexive, asymmetric, and transitive.
Okay. Well, let's see. It's
Isn't that
a good
I mean,
thing to look at. Let's look at partial order, PRTIA order, and yeah. So a partially ordered set from Wikipedia. It's it's reflectivity, antisymmetry, and transitivity. I think that's also Wolfram. Math also says the same thing. But you're driving right to the point, right to a point where I think is very important, and that's, I think if you use the idea of a partial order as it applies to sets in this type of work, that you greatly over-constrain the application, of this work, because reflectivity is basically the standard definition. But it really, for structural modeling, only the symmetric component really matters for the structure. And so reflectivity really shouldn't come in. It doesn't matter if it's irreflexive, non-reflexive, or reflexive. Shouldn't impact the structure of the system. Does that make sense?
Yeah, that does. What about antisymmetry versus asymmetry?
Well, antisymmetry is has a if statement in the middle of it.
Yeah.
And so it says if you have this condition, then you have these three logical properties. If you have that condition, then you have three different logical properties. So that there are two groups of logical properties and a if statement. So a lot of uncertainty in antisymmetry. And so we don't allow it because it just creates complexity, because it has completely different logical groups, and it has uncertainty associated with it.
So are there when you have you list set? Yeah. So I understand that. So these are the two sets of properties depending on how you answer that conditional, right? Set 1 and set 2?
Oh no, that's not.
No.
No, no, so in the anti-symmetry has equivalence relation, which is reflective, which is reflexive, symmetric, and transitive. And then it also has, at the core of it, it has an order, which is could be reflexive, irreflexive, non-reflexive, asymmetric, and transitive. So in the partial order itself, it restricts, for the ordering component, it restricts reflectivity, it restricts that to reflexive and asymmetric. But what I'm trying to point out here is it could easily be irreflexive and asymmetric or non-reflexive asymmetric, because the reflectivity doesn't really matter on the system structure. And transitivity really doesn't matter on the system structure. Transitivity is very important for the economy of solving the problem. But you could gain the information about the structure of a system just by using empirical information and no logical inference. It'd be much more expensive. But so transitivity really doesn't matter. And transitivity rides basically on top of the symmetric connections. So that's why we say in the AMEI that the symmetry is the most important for the structure. It is the one that dictates the structure. Okay, we've got about 8 minutes left in this round. Let's see. Then I just go through, and this is basically the little part that we put together. I think for next time, for May, I'm going to try to have a GitHub type of, whoops, wait a minute. It's not the one I want. I want this. There we go. Let's bring this one up. So I'm going to try to clean up what I have now, add the test to it, add some more, a little more documentation, and have it available on GitHub for the May using this particular north of.
I think it's interesting that the direction you went in what you just described to the sets of relationships that better matched linguistic relations, whereas the material that I've been looking at in studies of psycholinguistics and ontologies and at least in the world of part-whole relationships, the direction was people trying to restrict language to find the ones that more align with a particular set of properties rather than including the non-reflexive, non-transitive. So it's interesting, you're opening up to ambiguity, and most of the stuff that I've been was looking at is trying to restrict the ambiguity in the use of the language. So it's, I think that's I hadn't realized that that's what you were doing before.
Yeah, so the 27 logical property buckets, right? Those give you big buckets to address these logical properties, where in set theory, you're highly constrained. And people go through all kinds of contortions to try to match what they're naturally thinking about and expressing in natural language to that set theory. So that's why I think that it's really important in structural modeling that we understand that, and that we simply provide this 27 by 27 initial topological base to start sorting this out, because the key on that particular tool is it can match natural language to structured graphics and mathematics directly. And and of course, when we're looking at like graph theory, we have and we're putting that together. Then the advantage of that, one of the advantages I think we demonstrated last month, is you can go and use the tools that are developed by the professional mathematicians that they make available to augment your work, to generate graphs, to check your work, all that kind of things that you can do once you start looking at a larger set of relationships. So yeah, that's the idea. You're getting it, Kevin. Next month, go ahead.
We talked about assembling examples, and right. I think a natural thing is to pull examples from published documents, and that also puts us in a position to offer a review paper. And a review paper that covers, the extant examples is a type of paper that gets highly cited.
Okay.
My question is, what is the format that we express the models that people have reported? And
right. So that's an extremely good question, and there's many different ways you can do that. One of the things that I would like to do, and what I thought about, is to actually take a little bit more of a historical approach and start with the work that Warfield did in his classifications, in his publications.
Yeah.
Then look at the variation that went with Sage. Sage started the variation in the mathematics and the technique.
Yeah.
Then Stewart in '85 started another variation in the mathematics and techniques. Then Hitchens, I think in the late '90s, did another variation, and the SPDP is another variation, right?
Right.
So I think, if we just try to do a tree, a branch tree, it says it started here, and then these appear to be the variations that came off of that, and then relate that back to the mathematical properties and mathematical capabilities that were listed by Warfield. I think he only did about 5 or 7 of the 27 logical buckets, and he listed. So, and then other people, based on that, kind of did different things. And then there's that fellow down at Portland State, Ludras or
Ledyard.
Yeah, Ledyard. Yeah, and so he kind of does kind of a little bit of overview analysis, but doesn't really have a structure in it. So if you would like to, work together to start outlining something like that, I think that would really be great. I look forward to doing that.
Yeah, I think that's a kind of a good strategy. Walking through historically is a good way, because then you can see where a lot of current papers might have picked their current approach. Like I see a lot of things that are coming out of India where they're doing it manually.
Right. So that's okay. I got those. So I got Public Policy and Analysis and Design from India book sitting right here, and that's exactly it. And they say Warfield, and they do Sage. I mean,
Yeah, so
so
being
they,
able to categorize the different styles would be useful. But my question about format was the actual file format of the matrices.
um,
How do you do that? Because if
well,
we have a collection of test files, we would want to know where they came from, which paper they were published, maybe
yeah.
some
Well,
classification of what is the
I,
matrix that we have, and
so yeah, we can if you get some target matrices that you think we should use, then I can put those into a JSON text file, comma separated variables. I can put it into a number of standard formats. I can put SQL. We can do all that. We can offer multiple verified, data files. And that's that could definitely be automated. And I've kind of started along that path with some matrices I do have on my site. So, and I have a lot of them actually in my test cases that I've never distributed to anybody. But those were more of a DSM and files from Hitchens and files from Warfield. But I have a number of them. I don't have SDDP or ISM complete ones very much. So if you could, if you had other ones that were available, then that would be good.
yeah. Well, I have a lot of papers on ISM, and maybe
Okay.
I'm not sure if I still have a Dropbox account, but there's too many to email, and I think
Well,
copyright-wise, you have to decide you want to use it for research, and then you can download it from my Dropbox.
okay. Well, I've
And
decided I want to do that. And if you could like pick the maybe top 5 and the top 10 papers you think will be, like the leaders in that particular case, and we could take a look at that, think about it.
the top 5, I would have no idea how to pick them. I have hundreds, a couple hundred papers here.
Okay.
That's why.
That's
That's
what
what
I
I'm.
would. That's what I figured. So, well, what we're looking at is do they all have a mathematical? Are they all of the same mathematical quality? Do they all give the same mathematical detail? So, what we're interested in is the mathematics and the matrix representations and the approach. So, I would say that one of the discriminators to select would say, okay, which ones seem to have the best mathematical approach and presentation.
Yeah.
Because I've read some of this stuff, and it goes along, and then they start with a kind of a standard approach, and then it's a miracle happens here, and they give an answer, right? And I
Right.
can never follow it. So anyway, it's something to think about, and we can definitely, and we should target some type of publication venue. You thinking of an area that we'd like to publish something in,
You mean a journal or?
or whatever?
I think targeting a publication in one of Warfield's original journals, the Transactions on Systems Man and Cybernetics,
Okay.
would be one. Uh,
Okay.
Journal of Technological Forecasting and Social Change might be another one.
Okay. So
Yeah,
general.
I would go after and say now here's a 40-year review of where Warfield stuff has gone. There's been different instantiations of it, which have these variations. There's different versions out there without people really stating what they're doing. There's a
Right.
lack of standardization. I mean, we've thought enough about this to make a case, and now if we just set up some processing engine to take things from the papers, put it in the format for you to deploy. So
Sounds like a good plan.
Yeah.
Sounds like a good plan. I'll let you take some time to think about that. Next month I'm gonna be working through and getting this particular software in the next level of refinement, and hopefully get an initial deployment on GitHub, and then we'll go on to the rest of it.
Okay.
So we're over our time now by about 5 minutes. So
All right.
we're in an interesting discussion, and look forward to next month's discussion in May. Let's see, that will be May what? That will be May, yep, May 7th.
Okay,
All
Joe.
right.
We'll see you later.
Take
Bye,
care.
Mary.
Bye, Jen.